Chapter 9c, flow problems. Problems are problems that are concerned with the transfer of material. Can be a problem like maximizing the amount of water that can pass through the network during a certain time period. And when we do that, we of course use directed graphs, so it's only going into one direction. The flow of material from one point to another, the material flows from one point, which we call the source, to another point, and we call that the sink. Of flow problem directed graphs are called capacities, right? So the little number along the edge, or what we called arc before, is in a flow problem called capacity. So, and what we want to do is we want to determine or to solve a maximum flow problem. That means if, let's say, we're talking about pipes, if the pipes of different capacities are connected, one after the other, the maximum flow through the pipes is equal to the minimum capacity of the individual pipes. What I would recommend to you now is to pause the video and read through page 385. There's some nice pictures which explain this relationship in a bit more detail. If you think you're good with this, just continue to watch. Okay. Next thing I wanted to do is have a look at example 7 on page 386. So I have drawn this example here for you. We have a directed graph. We're having vertices A, B, C, D, E. So don't have a look at the green one yet. That's for question C. We want to investigate the maximum traffic flow from A to E through C. So we're having 5 cities here, and this is the amount of cars which goes through there or can go through there in 1 hour. We want to have the maximum traffic flow from A to E through C. Okay, good. We're going from A to E, but we need to go through C. Good. So this is a 300, a 600, and an 800. And we said before that the maximum can only be the minimum capacity, right? If 300 go through here in 1 hour, 300 cars, there's no way that there's going to be more than 300 going through here or reaching E in 1 hour. So that means the answer to the first question, the maximum traffic flow from A to E through C, is 300. So what we want to do now is question B. And question B, we want to investigate the maximum traffic flow from A to E overall. Okay, so there are 2 options. As I said, don't have a look at the green one yet. We can also go from A to E over D, right? And the minimum here is 150. So when we talk about overall flow, we would then add those 2 numbers. So we would have 350 plus 150. 300 plus 150. So that means the overall maximum traffic flow from A to E is 450. So we just add the 2 smallest numbers. Now we can have a look at the green arc here. We have a maximum flow and we want to go from A to E overall, including this new road from D to C. So as we had 300 before, so 300 is the flow from A to E, and the capacity from C to E is 800. And there now, through the green road, can come another 500 cars, because here we have 500 and here we have 500. If the cars go this way, we have 300 coming out of this direction and 500 coming out of that direction. So the actual 800 from C to E can be used here. That means the new maximum flow for C to E, or for overall from A to E, due to this new road is going to be 800. 800 cars per hour. Okay, again, we had 300 over this way already, so there are 300 coming. That is the maximum capacity because it's the smallest number. But now the new road enables us to get 500 cars through there per hour. So it's all they're all going to see 300 from here, 500 from there, but 800 actually can fit on there. And as we're talking about overall capacity, we add those two numbers, 300 plus 500, and we actually can do the 800, which are possible along that arc. Good. So how can we deal with maximum flow is by using cuts. Okay, so we're having a network, we're having our diagram, and what we can do now is we can divide the network into two parts by separating the source from the sink completely, right? And then what we do, we have to have a look at the cut capacity. At the cut capacity, and that's the sum of the capacities of the arcs that are cut. This includes only arcs that flow from the source side of the cut to the sink side. So we need to have a look at the direction. The minimum cut capacity possible for a graph would be the maximum flow through the graph. That sounds a bit weird, but when we do this example here, example 8, that actually makes a lot of sense. So we want to cut this graph so that the source is going to be separated from the sink. Okay, we're going from S to T. And we want to separate them completely, and we can do that by cutting along here, right? Let's say let's cut one. And we can do that if we also cut along here. Then we would also separate them. There are more options. We could just cut through here. Okay, so, or we could cut through here. So that means we actually have 4 options. And we now have to investigate each of those 4 cuts. Okay, if we do cut 1, the capacity would be 15 and 20. So we add those two up. 15 plus 20, that's 35. Okay, cut 2. Cut 2 would cut through here, that's a 14. Also through the 6 and to the, through the 20, okay? But we don't, or let's say we neglect the 6 here because that's the wrong direction. It's not flowing to the sink. So we only have to take into account the 14 and the 20. 14 plus 20 is 34. Good. What's with cut 3? If we cut through here, we have a 14 from there, a 15 from there, and a 20 from there. So we add them all up. 14 plus 15 plus 20. Oops. And that is going to give me a 49. And what's with cut 4? We're cutting through here, that's a 10. We're cutting through the 12, but we neglect that again because that's the wrong direction. And we're cutting through the 20 here. Okay, 10 plus 20. And that is a 30. So now we've had a look at the different capacities and we've calculated cut capacities. But what's that now used for? We want to have a look at example 9, calculating minimum cut, maximum flow problems. So we would do that again. We would investigate all the cuts possible, and that's on page 389. And then, like in the example before, we would add all the numbers up. And then we would choose the option with the minimum, so the minimum cut capacity, right? Have a look at our example above here. The minimum cut capacity here was 30, so that's the lowest number. And that would again allow for the maximum flow, right? So have a try with this example. You see it's worked for you in the textbook. Do the same thing, cut it wherever possible and add the numbers up, and then the lowest sum will give you the maximum flow. So the minimum cut will give you the maximum flow. And then there's also example 10 on page 930, which I want you to read through. And then I want you to have a go on exercise 9C.